plus million years old, and the Antarctic line of it is between 7 and 8 million years old. It's been there a very long time. I said I'd come back to mosses. Mosses have looked as though they might be recent colonists based on the endemism pattern, but mosses are also a bit different to higher plants in that they're parthenogenetic plants. They don't rely on sexual reproduction, or they don't have to rely on sexual reproduction. Some species are cosmopolitan. This moss here, Bryum argenteum, is cosmopolitan. It gives a tool to look at its dispersal, its colonization history, its adaptation. This is very recent and ongoing work. And looking at specimens of this from the Antarctic Peninsula, from Victoria Land, it's been present in Antarctica for at least 500,000 to 4 million years, and actually has colonized Antarctica on 3 separate occasions at least in that time. So again, even mosses are turning out to be ancient. Now, I've got a couple of things I want to raise just before I finish. Now, everything I've talked about so far in biology has been in the context of ancient biology. But it is reasonable to ask, how do things move around in Antarctica? And the first step to do that is to look at how they move around in the current or the recent past. Things like mosses have very small spores. Lichens have very small spores. Tardigrades have these little tiny things called tongues, which are dried out tardigrades, a few tens of micrometers long, a few tens of micrograms. All of these things can get in the atmosphere, as can bacterial spores or bacterial cells and so on and so forth. So aerial dispersal is often imputed as the means things move around into Antarctica and within Antarctica. If you think about what happens as ice recedes at present, it exposes new land. Anybody who's been around the Antarctic Peninsula will have seen this. That new land is very rapidly colonized by a microbial and a plant and invertebrate community that is very typical of that area. Plainly, things can move around. It's not that they're fixed to a spot. The question might be, how far can they move, and what are the boundaries between the regions that they can move within? So this is just to put up as a taster. It's some work with one of our postdocs in Bath has been doing with me. The center of the squiggly line maps is Signy Island in the South Orkney Island. And every line on that map is simply a 24-hour trajectory of where an air mass goes to after it's passed over Signy Island. And you can see the majority goes somewhere between northeast and southeast of Signy, as you might expect in the prevailing winds. But occasionally you get a storm track that goes a completely different direction, like the one that goes to the base of the Weddell Sea. So this sort of analysis gives you an idea of the sort of proportional connectivity there are between areas. And if you illustrate it in a different way, as these maps do, this basically it looks at a probability density of where an air mass is going to get to within 24 hours of a starting point. Top left, the starting point is in Tierra del Fuego, and you can see that, okay, most things go somewhere between north and south heading eastwards, and it touches the tip of the peninsula. 95%, or let's say about 5% of air masses do get from Tierra del Fuego to the Antarctic Peninsula within 24 hours. Same thing, the bottom left, from the tip of the Antarctic Peninsula, air masses don't, or within 5%, air masses don't get to Southern South America. So there are differences depending on your starting point. The bigger map on the right-hand side shows similar sort of density maps at different starting points. So Tierra del Fuego, the South Orkney Islands, and then the tip of the, South Orkney Islands, South Georgia, tip of the peninsula, Central Peninsula, Alexander Island. You can see as you go further south, there is an increasing chance of westwards dispersal from a point on the Antarctic Peninsula. This sort of analysis hasn't progressed very far, but it gives us an idea of connectivity between regions. And that's the sort of thing that's relevant to contemporary colonization and colonization over the last few hundred to few thousand years. And one final thought for you. I put up the map that showed continental, maritime, and sub-Antarctic. This map shows you the current view of patterns in Antarctic terrestrial diversity. Alex Terrodes and a community of people from the then SCAR EBA program did a very detailed analysis looking at biological distributions, relating them to geological and climatic factors and so on. And actually, not surprisingly, you get a far more complex picture of diversity, regionalization in Antarctica. These things are called Antarctic Conservation Biogeographic Regions, ACBRs. And these are currently the basis of SCAR and the Antarctic Treaty System's plans for developing conservation strategy for the Antarctic. My point in putting them in here is that we have 15 of them in the Antarctic already, and that's before we take into account the South Shetland Islands, the Sub-Antarctic Islands, and so on and so forth. Sorry, South Sandwich Islands, I meant to say there. So Antarctic biodiversity is far more complex than that simple three-way split that I put up at the start. That shouldn't surprise us. Antarctica is twice the size of Australia. Why should it have one biology? But we're now getting to a point where we can document this and we can describe these regions. Anybody interested in operational matters or conservation matters, an alarm bell should ring immediately here. Every time you move between a region, there is a risk of carrying things that are endemic to one region or indigenous to one region into another region in which they're not indigenous. So this is very relevant to anybody with interests in biological invasions and movement of species around. Anyway, I wanted to flag that. I didn't want to go into detail on that. My final slide, to give you an overview what I've been talking about. Our current paradigm, our current understanding, is that much Antarctic terrestrial diversity is ancient in origin. And that basically means it's been there a long time, it's radiated in evolutionary terms where it is now rather than colonizing, and that local radiation rate far outweighs the colonization rate, even for microbial groups, which comes as quite a surprise. Plainly, if we have life on land, land needs to be there for the life to live on, and that means there is a new impetus to linking between biology and glaciology to understand the distribution of ice and the distribution of life on the Antarctic. And it's a two-way interaction. Both sides can form the other. There is far more complexity and regionalization in Antarctic biodiversity than we'd ever suspected, and that's coming out very recently. And this in particular provides a very practical challenge for conservation and governance in the Antarctic, so to the Antarctic Treaty System, basically. As an example, if we think of Antarctic Specially Protected Areas, ASPAs, as national parks or something like that, and we think of what they're meant to protect, across the entire Antarctic, vegetation is protected in a total of about 16 square kilometers of the continent. And half of that is within a single protected area. I think that protected area is Bias Peninsula on Livingston Island and the South Shetland Islands. Clearly, there is a very big conservation challenge here. On that note, if anybody can hear me, I will finish, and we'll see whether anybody's got any questions, or if nobody could hear me, we'll work out what to do next.
Okay, Pete, thank you very much for the talk. It was only a few times you cut out earlier on, so we got most of the last part of your talk, and we could see the slides.
Okay, it's very hard to tell because I keep getting things saying my audio, or not, the audio link has died here.